Okay, so final conic section is the hyperbola. That's the final big box. It looks very similar to the ellipse, but it has a subtraction sign instead of an addition sign. So it's a lot easier to identify what A and B are. B is the thingy that's being subtracted. You do the positive thing first. Quick definition of a hyperbola. It's two opposing parabolas. The idea is that if you go from the foci to the difference of whose distance from two fixed points, the foci is constant. So if you do this minus that, it's the same. So you subtract the distances instead of add them together. That's why I kind of like it's that oval, and then it just kind of undoes itself. So oval undone. It's kind of what happens. So what we're going to do is we're going to kind of graph one. These things are a bit of a pain, and my computer's freezing. These things are a bit of a pain to graph. So there's the graph. I already did it. But I'm going to talk to you through where we get the stuff, and I'll show you where it's showing up on the graph. Don't worry about graphing these things. They're kind of a pain. So let's not worry about that. So when we're trying to figure out what sort of hyperbola this is, we see who's being subtracted. So the x squared is being subtracted. So that looks like this one down here, where the x is being subtracted instead of the y being subtracted. So our center is going to be at hk. So we got to figure out what our h and k are. So, not h, I would like a k, please. So k is always with y, so y minus what is going to be y? Well, 0. Here is our h, so it's 0. So our center is at 0, 0. You can see that point right there, 0, 0. Next, we've got to figure out what our a and our b are. So our a goes right here. So, but that's a squared, that 4. So regular a should be 2. Our b is going to be where the 9 is, but that's b squared. So we want to use 3. Now we got to figure out c eventually, but you might notice this time we do have a normal Pythagorean theorem. C squared equals a squared plus b squared. So the way the Pythagorean theorem is meant to look. So when we're looking for our c, c squared equals a squared, 4, plus our b squared, which is 9. So c is plus, or no, just the square root of 13. Okay. And that's telling us our distance from the center to the foci, center to foci. I forgot to mention this earlier, but since x is being subtracted, we're going to have a vertical transverse axis. So I could have written that down a little while ago. And that's telling us that see all these points, see all these cool points right there? They make a nice tall line. They're all vertically stacked instead of horizontally stacked. Our vertices are going to be located at h comma k plus or minus a. So our h is 0, our k is 0, so when you do plus or minus a, so that's plus or minus 2. Close that off. So you can see our two vertices here. One is 2 up from our center, and one is 2 down from our center. Our foci are going to use a very similar formula. It's going to be h comma k plus or minus c. I'm just copying that off the formula paper. Should always have that handy with you, kind of like our trig identities paper. Oh, so it is at 0 plus or minus the square root of 13. And the square root of 13, it's about here. It's a little bit more than 3. Not quite 4, because that'd be the square root of 16. Now, you might have noticed these two. These are the B spots, so they're away and away. And what it does is you use these and you make a vertical line and a vertical line, and then you use these and make two horizontal lines, and then they sort of make a box. And then you draw an X through the boxes. Those are asymptotes that these parabolae approach, but they don't quite reach. So it's kind of a pain in order to make that graph. So don't really worry about graphing these things. Well, we can graph the other ones, but these ones are kind of, yeah. So it's just dotted lines upon dotted lines upon dotted lines. And it is just a mess. Okay, that's it for graphing. I'm going to do a video break here, and then I will see you in converting to standard form.